we reached up to this point and now we want to integrate. So see this z to the power n, and we want summation z to the power n with some coefficients. So these coefficients we need to identify. Okay. So what is this? Can you identify this? Alright. So this is nothing but, so this is equal to now summation n from 0 to n minus 1 integral fs upon s raised to n. Remember now this is Cauchy integral formula because 0 is inside this. So this is nothing but nth derivative at 0 because this is power n plus 1. So this is nth derivative of f at 0 upon factorial n, z to the power n. How do you get this? Let me repeat this again. So suppose I will write here. So this formula, that is nth derivative of at some point z naught, is nothing but 1 upon 2 pi I to n factorial integral c fz upon z minus z naught to the power n plus 1 dz. This we are applying for 0. So nth derivative at 0 upon factorial n is nothing but what? 1 upon 2 pi I integral over c fz upon z to the power, because z naught is 0, z to the power n plus 1. That is what exactly we are getting. Here the variable of integration is ds, and you may take 1 upon 2 pi I here. So everywhere you have 1 upon 2 pi I and 1 upon 2 pi I. Okay. So this is nth derivative at 0 upon factorial n plus this entire thing I will call as rho nz. And then if we show that rho nz tends to 0 as n tends to infinity, then we saw that this right hand side will converge to this series, actually 0 to infinity, because this is partial sum and this is remainder term. So remainder term tends to 0 if and only if this series will be convergent. Okay. And remember our left hand side was fz. So fz will be all that, because fz is this integral, and that is exactly the left hand side of this also. Okay. So this is nothing but fz actually. That equation, see again, show this equation again. This is fz. That same equation I have written here. Same equation I have written here. Only thing is now that I have actually found out this integral 1 over s minus z I have substituted appropriately. Now to prove that this rho nz tends to 0. But for this rho nz going to 0, we have to see what is rho nz actually. So let me write this rho nz separately and show that it goes to 0. Alright. So what is this expression for rho nz? So where rho nz is this expression, that is z to the power n upon 2 pi I integral over c fs upon s to the power n s minus z ds. Now when you want to estimate an integral, what is our standard trick? Standard trick is to use m into L theorem. Okay. So now what is this curve C? Let me draw that picture again, which is now erased. So let me draw this picture again. Okay. What was C? So C was so this point 0 is here, then this was capital R naught. Okay. The point Z is here, which was small r naught, okay, and then this was r, okay. So we choose this R naught and R, so that R naught is between R and, so this was R and this was R naught, and S is here, okay, S is here and Z is here, alright, and this is our C. So mod of S minus Z is bigger equal mod of mod S minus mod Z. So mod S is R naught, but then this is bigger than this, so I can directly write R naught minus R. Okay. So 1 over mod S minus Z, so now I am trying to estimate this integrand. So mod Fs will be less than or equal to some C, because on this C, F is analytic, so in particular it is bounded on this, it is continuous on the closed and bounded set, so it will have upper bound. Okay. That theorem also we saw, if you remember, by uttering the word compact, but then you can forget this, a curve with a closed and bounded set. So on that, a continuous function has an upper bound. So there is some constant m anyways, such that mod Fz or Fs is less than or equal to m for all S in on this C. So on C, mod Fs is less than or equal to some m, then 1 over mod S minus Z we have just now estimated, because this mod S minus Z is bigger equal this, therefore 1 over that will be less than or equal to 1 over R naught minus R. What remains is the S, but S is exactly, mod S is nothing but R naught, okay, and Z is R. So we have all the estimates, now, and then this length of C is 2 pi times R naught, okay, 2 pi R naught, because this is radius is R naught. So this mod of rho and Z, now I am in position to estimate. This is less than or equal to mod of this is R naught to the power n, R to the power n, so mod Z is R. You have to continuously show this picture, okay. So mod Z is R, so this is R to the power capital N. This, if you take mod, then this will become 2 pi. Mod Fs is m, S is R naught to the power n, and mod S minus Z is 1 over R naught minus n, R. Just now we have shown 1 over R naught minus R. And into length of C, this is m, into length of C is what? Length of C is 2 pi R naught. So 2 pi times R naught. So the factor that depends on n is R to the power n by R naught to the power n. Okay. So this bound is, this 2 pi will get cancelled. So m R naught by into R. The important factor is R by R naught to the power n. And as R naught is bigger than R by R naught is less than 1. So now this, as n tends to infinity, will go to 0, because R naught is bigger than R. See this picture again. R naught is bigger than R. Now come here again. So R by R naught is less than 1, and therefore this will go to 0. So this goes to 0 as n goes to infinity. So mod rho and Z goes to 0. Now come to this side again. So we have shown this. So series on the right hand side, okay, this as n goes to infinity, this goes to 0, means this series with n from 0 to infinity converges to Fz. So we have shown that Fz equal to, so thus summation nth derivative at 0 upon factorial n into z power n from 0 to infinity, because whatever was remainder term we have shown that it goes to 0 as n tends to infinity. So this series expansion, this is Maclaurin's series expansion, so called Maclaurin's series expansion. Alright. Now this is around origin and powers are also z minus 0 to the power n. So in general we can have z minus, here we can have z naught and powers of z minus z naught, that is z minus z naught to the power n. Okay. But that is just shift of origin or something like that. So how do you do that? I mean, consider the substitution or whatever, consider the function which is analytic at z naught instead of 0. This function we assume to be analytic at 0 and then therefore expressed as a power series around 0. And then since it is analytic at 0, the derivatives of all orders at 0 exist. So this was all done at point 0. From 0, if we want to go to any point z naught, then the trick is just shift, that is now let case 2 is, instead of 0, case 2 is let f be analytic in disk z such that mod z minus z naught is less than r. Now we have taken general point z naught. Okay. Now consider the function gz equal to f of z plus z naught. So z plus z naught minus z naught is suppose less than r, then at those point g will be analytic. Okay. So mod, so g is analytic in z such that mod of whatever is the whatever points f is applied to z minus z naught, okay, that I have put here. So z minus z plus z naught minus z naught less than r, that is in z such that mod z less than r. That means now we have a disk around origin. So we have again come to origin now, and then we want to use our earlier theorem for g now. Is this clear? So around origin we already have expansion, so that we will apply to g now. So gz will have Taylor series expansion around origin. Is it clear how the problem is converted to earlier case? So this is now general case where f is analytic in the neighborhood of any point z naught. Where if it is analytic at 0, then we have already obtained the Taylor series expansion. But from such function we have constructed a function which is analytic in the neighborhood of 0. So by case 1, g has Taylor series expansion. So by case 1 now, by case 1, okay, g has Taylor series expansion. You may write Maclaurin's, alright, but then because g is around origin, and that will be what? Gz equal to summation nth derivative of g at 0 upon factorial n z power n, because this is around 0. Just like f, here we have applied to g because g is analytic in the neighborhood of 0. Now gz is what? F of z plus z naught. That was our definition of g. G was what? F of z plus z naught. So now this was what? This is, now what is nth derivative at 0? So nth derivative of f is nth derivative at 0 is nth derivative at z naught. So this is nth derivative at z naught divided by factorial in series. G and f are just this. So nth derivative of g at 0 is nth derivative of f at z naught. 0 to infinity and z to the power n. Now if you substitute z plus z naught by z, then z gets substituted by z minus z naught. So you put z equal to z minus z naught, then this z naught will cancel and you will get f. So put z equal to z minus z naught. So this you will get fz. Okay, z plus z naught, z minus z naught plus z naught, so you will get z, and then z is replaced by z minus z naught, so you will get nth derivative at z naught. I mean, this is somewhat slightly notationally not correct, but then what I mean is that put z here, but then you have to replace this by z minus z naught, that's it, nothing else. So just you may ignore this. What I want to say is z plus z naught is replaced by z, but then on this side z will get replaced by z minus z naught. So this is general Taylor series expansion around z naught, where z naught is any arbitrary point where f is analytic. All right. Now let us see some standard examples of Taylor series. Once we have this formula that we have to just compute nth derivative at that point, okay, around which the Taylor series expansion is to be found, then you may take standard functions, and if you know the formulae for the derivative, then you are in position to find the Taylor series expansion. Okay. So how to do that? So let's see how to do that. All right. So some examples let us work out. So let us consider e to the power z. Okay. So consider fz equal to e to the power z. Now you want to subscribe a point, that is around which point you want the expansion, and then the condition is that the function should be analytic at that point. But e to the power z is entire function, so you may choose any point because it is analytic everywhere. Okay. So to start with, let us consider 0. That means let us find out the Maclaurin series. So let z naught be 0. And f is analytic everywhere. Okay, so f is analytic everywhere, in fact, everywhere. So the condition of the Taylor theorem is satisfied. Condition of the Taylor theorem is that f should be analytic at z naught. Okay. Then it is analytic in some neighborhood, and for points in that neighborhood, Taylor series expansion is valid. Okay, so that is the Taylor's theorem actually. Wherever f is analytic, you can expand around that point. So now, for example, this function e to the power z is also analytic at z equal to say 1 plus I. So can we expand e to the power z in the powers of z minus 1 plus I to the power? Yes, we can do that. Only condition is that f should be analytic at that point. And where the expansion will be valid? Expansion will be valid for all those points in the neighborhood of point z naught where f is analytic. Okay. But then there has to be some neighborhood, because by definition f is analytic at z naught means there is a neighborhood of z naught in which f is analytic. Once the condition is satisfied, then we have to just find out now nth derivative at origin. So what is nth derivative of f? But with e to the power z we are always very lucky, because e to the power z derivative is e to the power z, all derivatives are e to the power z. So nth derivative of e to the power z is again e to the power z, and therefore nth derivative at 0 is 1. for all n. Okay. For all n. Now substitute. Now substitute in the formula for the Taylor series, that is nth derivative, so this formula. Okay. Now substitute here. So e to the power z, see this formula. Now nth derivative is 1. So 1 upon n factorial z to the power n. Is this clear? So this is the same Taylor series expansion as you had in case of real variable. You substitute z equal to x, then you get x to the power n upon factorial n, and you understand that the same analysis going on. That means what about sin z and cos z? Okay. So let us obtain cos z. Okay. So let us obtain cos z from e raised to z. Do you remember formula for the cos z in terms of e to the power z? Because sin z is, okay, so let me write formula for cos z. So find Maclaurin series expansion maybe for cos z. Let's do that. Okay. Shall I give you 2 minutes? See, one way is you find nth derivative of cos z, or you may use e to the power z and express cos z in terms of e to the power z and substitute. Okay. At present we will assume the manipulations with the series, that is you can substitute one series in the other and so on. Okay. So shall I give you 2 minutes? So I give you 2 minutes for finding the Maclaurin series for cos z. Okay. As such expression you already know, I suppose, from the real variable, but then how do you obtain it in complex case? That means you write down. Okay. So I will give you 2 minutes. Okay, let's start. So, suppose fz, I denote cos z by fz. Then what is first derivative? First derivative is minus sin z. Okay. So f dash z is minus sin z. F double dash is minus cos z. Third derivative is sin z, because cos z derivative will be minus sin z, minus minus plus. Okay, sin z. And fourth derivative will be cos z. and then the next derivatives will repeat because you already get now cos z again. Okay, so fifth will be minus sin z and so on. So whatever will happen to the first four, after that the coefficients will repeat. Okay. Now what is first derivative at 0, because we want to find Maclaurin series, so nth derivative at 0 we want. Okay. So first derivative at 0 is 0 actually. Okay, first derivative is 0, second derivative is 1, third derivative is 0, and fourth is also, second derivative is minus 1 and fourth is plus 1, because this is cos 0 is minus 1. So let me write these derivatives here. Okay. Let me write these derivatives here. That is, of course, f0 is 1 because this is cos. F dash 0 is 0 because that was minus sign. F double dash 0 is minus 1, and the third derivative is 0, and fourth derivative is 1. And then again this sequence repeats, 1 0 minus 1 0, 1 0 minus 1 0, and so on. Okay. So definitely the fifth one will be 0, seventh one will be 0, so odd coefficients will be 0. Okay. So there won't be powers, odd powers of z. Okay. There won't be any odd powers of z. And then even powers will have alternate signs. So first 1 minus 1, 1 minus 1. So it is clear what the Maclaurin series will be. Okay. So the nth derivative will be, so second derivative is 0. Okay. So it is 4n or 4n plus 2. That's it. Okay. I mean 0 mod 4 or 2 mod 4. 0 mod 4 it is minus 1, 2 mod 4 it is 0 mod 4 it is 1, and 2 mod 4 is minus 1. That means if you divide by 4, remainder is 2 or 0 if the number is even. Okay. Anyway, you can just take alternate ones. So cos z is f0 is 1, then minus z square by 2 factorial, because z raised to n, this derivative is minus 1 upon 2 factorial, third will be 0, and fourth will be plus, as we have found it here, and then sixth will be minus, and so on. Okay. So this will be nothing but minus 1 raised to n z raised to 2n upon 2n factorial. So this is nothing but summation minus 1 to the power n z raised to 2n upon 2n factorial so this is z equal n equal to 1, it is minus sign, n equal to 2, it is plus sign, 3 it is minus, like that it is. So this is Maclaurin series expansion for cos z. Okay. Similarly you can find sin z, so I leave that to you. So find for sin z. Another way is that you can substitute cos z, you can write cos z in terms of exponential function. So you know the formula. What is formula for cos z? In terms of e power z, it is e raised to iz plus e raised to minus iz upon 2. So you remember this formula, we have done this long back. Now you have formula for e to the power z, okay, but then that you can put z equal to iz, z equal to minus iz upon 2, manipulate, and then you will also get again another way of obtaining this. What I mean is that this is summation iz to the power n upon n factorial. This 1 upon 2 I will take outside, and plus minus iz to the power n upon factorial n. Okay. And then z to the power n upon factorial n you can take outside, and I to the power n plus minus I to the power n, and then you check that for odd n this gets cancelled. So this is another way of obtaining. This should be, yes, that is correct. Okay. Similarly also you can obtain sin z by writing e to the power iz minus e to the power minus iz upon 2i, and then put the values and you will get the Taylor series expansion for all z. You may get Taylor series expansions of functions of the type say z square into e raised to 3z. So for example, if you want to find z square e raised to 3z, okay, so let us find it out. So find Maclaurin series expansion for z square e to the power 3z, suppose. That means what? That means you want to expand this function in powers of z, because Maclaurin's means not z to the power z minus z naught, where z naught is 0, that is z power n. So you want to expand this function in powers of z. First you write e to the power 3z. Can you write e to the power 3z Taylor series expansion? Yes, we know e to the power z, but that is valid everywhere. The Taylor series expansion of e to the power z is valid everywhere. So e to the power 3z, how do you write? It is summation 3z raised to n upon factorial n from 0 to infinity. Okay. That means that is equal to 3 to the power n summation 3 to the power n upon n factorial, okay, z power n n from 0 to infinity now I multiply by z square. Okay, so now I multiply by z square, so z square e to the power 3z is equal to, this will be z power n plus 2. So summation 3 to the power n upon factorial n z power n plus 2 n from 0 to infinity. Okay. So if you put n equal to 0, you will get term corresponding to z square. Okay. So now if you strictly want in terms of z, then you can shift this. That means you will get, you replace n plus 2 by n, you get by n minus 2, get n minus 2 factorial, but this sum will vary from this will vary over n minus 2. So n minus 2 equal to 0 means n from 2 to infinity. So this you can also write as n from 2 to infinity 3 power n minus 2 upon n minus 2 factorial z power n. If you want strictly in terms of, I mean if you want to see z power n here, right, but that means the first f0, f1, this starts with z square. So constant term and coefficient of z are 0, which is expected because derivatives of this will be 0, I mean function is 0 and first derivative will be 0 at 0. So at 0, so you see that f0 and f dash 0 are both 0. Therefore, it will start with f double dash 0 only. So this is how you obtain Taylor series expansion for this. Okay. Another variation is that you take the same function, but then around certain other point you expand the function. So suppose if you take e to the power z and you want to expand it in the powers of z minus 1, for example. Okay. So let's do that suppose. So find Taylor series expansion of fz equal to e to the power z around say z equal to 1. That means in the powers of z minus 1, in the powers of z minus 1. Now what is formula? For any point z0, it is nth derivative of z0 upon factorial n. So if you find nth derivative of a function at that point, then it is just matter of substitution. So now the function is there, point is given. So can we find nth derivative of this function at point 1? Yes, because e to the power z, no problem. So nth derivative of f at z is actually e to the power z, and then evaluated at 1, there is no problem, it is e always. All the time it is e. Now once you do this, what is Taylor series expansion? Then fz, we know that it is nth derivative at z0 into z minus z0 to the power n divided by n factorial, n from 0 to infinity. So this is Taylor series. Okay. So this you have already found. This z0 is your z0 is 1 now, because you want expansion in powers of z minus 1. But this is e. This e is, for any n it is e, so e will come out. So it is sigma z minus 1 to the power n upon n factorial into e will come out, because this is e. That is e to the power z. Function is e to the power z, but expanded around 1. That means it is z minus 1 to the power n upon factorial n, n from 0 to infinity, e outside, because it is expanded around 1. Now this expansion is valid where? This expansion is of course valid for mod z minus 1 less than infinity, because e to the power z is, so in the neighborhood of 1 you are expanding, okay. So this is 1 in the neighborhood of z, but then any neighborhood. So that means actually you can again put any value of z, because any neighborhood of 1 is allowed. So this is valid everywhere. The entire function, you have Taylor series expansion around any point, valid everywhere. Okay, is this point clear? You may take any z0, then theoretically the Taylor series expansion is valid in a neighborhood of that point z0 where it is analytic. But then if you take entire function and choose any point, then first of all f is analytic at that point, and what is neighborhood in which it is analytic? You may take whichever neighborhood you want. That means for any point z in the plane it is valid. Okay. Now another way of obtaining the Taylor series expansion around say z equal to 1, or for that matter any other point z0, is you write e to the power z, you may write e to the power z as e to the power z minus 1 into e to the power 1. Okay. Now this you expand, okay, this you suppose expand e to the power z minus 1, then it will be what? Instead of z you have z minus 1. So this you expand around origin suppose, then you get expansion of this around 1, that is suppose this is equal to some sigma z minus 1 to the power n upon factorial n from 0 to infinity into this e. Same thing you get. So this is another way of obtaining that, because e to the power z minus 1 is just putting z equal to z minus 1 in the earlier expansion of e to the power z, z minus 1 to the power n upon factorial n. Okay. Okay, let's do some more examples on the Taylor series. All right. So let's do some more problems. So find Maclaurin series for the following function, z upon z raised to 4 plus 9. So let me check what is that. Z raised to 4 upon z raised to 4 plus 9. Z upon z to the power 4 plus 9. Now some polynomial appearing in the denominator, so we need to be careful as to where this exactly is analytic. Okay. So let us so find Taylor series expansion of this problem you want to solve. So how do you go about that? Any idea? So see, typically in such problems you have to use Taylor series expansion of 1 over 1 minus z around origin. Okay. So first of all you have to note that. So note that the Maclaurin series expansion of 1 over 1 minus z is 1 over 1 minus z is equal to 1 plus z square, so on, and this is valid only if mod z is less than 1. Okay. So if mod z is less than 1. This is easy because you take derivatives of this at point origin. So what is derivative of your function is fz is this, okay, and then this is analytic at 0, and this neighborhood throughout it is analytic. See, mod z less than 1 means it is unit based around origin, okay, everywhere here it is analytic. So for any point z it has Taylor series expansion. Now only thing is that your point is 0 because Maclaurin series, and function is this. So you have to find what? The nth derivative. Nth derivative you want to find out. Okay. So suppose your function gz is 1 over 1 minus z. What is nth derivative? alright. So this is, let's find first derivative. So it is, alright. So do you know what is nth derivative? You want to compute? So I will give you 2 minutes. You just compute the nth derivative of this at say 0. So try to find first derivative, second derivative, you may guess the formula. You can write the nth derivative with it. So nth derivative is n factorial. Got this formula? Because first derivative is 1 over 1 minus z whole square. Alright, that if you put z equal to 1, then it is 1. Second derivative is 2 upon 1 minus z whole cube. That again put z equal to 0, then you will get 2. And then you can prove by induction that this is n factorial. So the Taylor series expansion of this around origin, that means Maclaurin will be summation n factorial upon n factorial, that is 1 z power n, n from 0 to infinity. But that if mod z less than 1. If mod z less than 1. Now coming back to our original function fz, we have to use this and somehow express it in the form 1 over 1 minus z. Okay. You may put z equal to minus z and write here minus sign. Okay. So you may have similar expression for summation n from 0 to infinity minus 1 to the power n z power n if mod z is less than 1. Just put z equal to minus z in this. So this is also useful formula and this may fit into that. Okay. So now I will take the z by 9 outside. So I will divide by 9. So it will come in terms of 1 plus something. We want 1 plus something. And then that z will put condition mod z equal to 1. Whatever z here we get. Do you understand this? So I divide the given function fz like this. So suppose your function fz was, let me write the function again for the convenience, z by z to the power plus 9. So I straightway take this z by 9 outside and you will get 1 plus z to the power 4 by 9. Why do I do that? Because I now get in terms of 1 over 1 plus something. Now 1 over 1 plus something is valid if mod of this is less than 1. So we want mod of z to the power 4 by 9 to be less than 1, or in other words mod of z to the power 4 less than 9. So in other words mod z is less than root 3. So this is valid in the root 3 neighborhood of origin. This radius is root 3. Then you can find Taylor series expansion of this function particular. Okay. Now how to find? Now it is easy because you just use the Taylor series expansion of 1 over 1 plus z, where your z is now z to the power 4 by 9, but you have taken already care to see that this quantity has absolute value less than 1. Okay. So now it is just z by 9 and you can write the series expansion of 1 over 1 plus z, which is given here. 1 over 1 plus z. Only thing is your z is, come back here, when your z is z to the power 4 by 9. Okay. So now substitute, okay, just substitute, that's it. So fz, which is z by z to the power 4 plus 9 is nothing but z by 9 1 plus 1 plus z to the power 4 by 9, which is equal to z by 9 into summation minus 1 to the power n z to the power n, but z is z by 4 by 9. So, z by 4 by 9 whole to the power n, n from 0 to infinity. So, this is z power 4n and this z. So, we will get z power 4n plus 1 divided by 9 raised to n into 9, that is 9 raised to n, actually 9 raised to n plus 1. So, this is whatever you get, now you have Taylor series, okay. So, this is minus 1 to the power n z raised to 4n plus 1, this z raised to 4n upon 9 raised to n into this 9. So, 9 raised to n plus 1, n from 0 to infinity. So, this rational function you have written as power series in certain neighborhood of 0, because this is in powers of 0. So, remember you have a rational function that is polynomial upon polynomial. So, it is not a polynomial, you have some non-trivial denominator, alright. But here on this side you have all powers of z, but this is not valid everywhere. I mean, this expression for this function is valid only in the root 3 neighborhood of z. So, let me write that if mod z is less than root 3. So, in certain neighborhood this type of expression for fz is possible. Okay. Now, one more type of problem is your standard, suppose 1 over 1 minus z you want to express as in some other say powers of z minus I or something like that. Okay. So, let us find Taylor series expansion of 1 over 1 minus z around I. So, find Taylor series expansion of 1 over 1 minus z around z equal to I. That means what? In powers of z minus I. Around origin means in powers of z. So, now we want on the right hand side z minus I to the power n, something like that. Okay. Now, how do you get powers of z minus I, because then somehow you should get z minus I somewhere here, but then I will take z minus of z minus I, that means you have added plus I. Okay. So, can I write 1 minus I minus z minus I, something like that? Okay. So, can I adjust this? So, I will adjust like this. So, 1 over 1 minus z I will adjust as 1 over 1 minus I minus z minus I, because this minus I plus I gets cancelled. So, you have this original fraction. Is this clear? That is what the adjustment is. And then now I will divide by 1 minus I. Okay. Now I will divide by 1 minus I. So, I will get 1 over 1 minus I into 1 upon 1 minus z minus I will write above there. So, you may take down this and then, So maybe I will write a entire expression again so that you can see in one shot. 1 over 1 minus z, first I wrote as 1 over 1 minus I minus z minus I. Just check whether it matches. 1 minus z minus I plus I gets cancelled. Now this is equal to 1 over 1 minus I outside into bracket 1 minus z minus I upon 1 minus I. Now why do I do that? Why do I do that? Again, because I get in terms of 1 minus something, 1 over 1 minus something, and that I know we have Taylor series expansion around origin provided this is less than 1. Okay. So this is valid if mod of this is less than 1. Okay. So now I can substitute 1 over 1 minus z by 1 plus z square and so on, provided what? This mod is less than 1. Okay. So when this mod will be less than 1, so consider this region where this mod is less than 1. Mod of z minus I upon 1 minus I you want less than 1. That means mod of z minus I should be less than mod of 1 minus I. But mod of 1 minus I is what? 1 plus 1 square root, that is root 2. So this is valid, whatever we write now is valid with in the circle with center at I and radius root 2. Okay, so we have this complex plane and this is I, okay, and then you have this circle with center at I, radius root, something like this. This is a rough picture, but this distance is suppose root 2. Okay, let me draw it. So let me draw the circle first. This is 1 plus I and this is root 2, wherever it is placed. Okay. This is I, this is I. Mod z minus I less than root 2. Okay, so now once this is done, you just plug in, that's it, 1 over 1 minus, now this is just a factor like z, we have taken care with the validity. So now just substitute. So 1 over 1 minus z now can be written as 1 over 1 minus I outside, and inside the bracket you have 1 plus z minus I upon 1 minus I, that is summation z raised to n, where your z is now this. So z minus I upon 1 minus I to the power n from 0 to infinity. Okay. So that is nothing but summation 1 over 1 minus I to the power n plus 1 into z minus I to the power n. This I have taken inside, n from 0 to infinity. So this is Taylor series expansion of 1 over 1 minus z around z minus I, valid in the region mod, so if mod z minus I less than root 2. Okay, so this is how it is done. Okay, so now next step is to obtain some kind of series expansion of functions where f fails to be analytic at z naught. Taylor series expansion is typically for the functions analytic at z naught, and then you express function as powers of z minus z naught. But if the function fails to be analytic at z naught, everything will collapse. You cannot have directly a series expansion in terms of z minus z naught. But then you do have, by again thanks to quotient integral formula, we do have some series representation, but that series representation we have powers of z minus z naught which are negative. So we don't get just powers of z minus z naught. Okay, we get z minus z naught to the power 1, 2, 3, similarly minus 1. So you will get negative powers of z minus z naught. Such series expansion is called Laurent series expansion. Laurent series expansion. and next time we will do this Laura series expansion and maybe some derivations which we can obtain from this. Okay. So that way we are coming to the end of the course now. After this we have to just compute the residues at poles, which is directly from this you can do. So the next important topic is Laura series expansion. That